In section 4, we will discuss probability. So the goal of probability in statistics is really to progress us toward the idea of inferential statistics, because as we've mentioned before, in statistics, when you do inferential statistics and you have to deal with error, the way that we deal with that error is through the idea of probability. So it's important that we have some understanding of probability before we get to inferential statistics. So this is really an intro section in terms of probability. We'll cover just some of the basics, kind of what the terminology is, and you should have read through that in the notes, and we'll go through some examples with just some of the basic probabilities and some of the rules that we use in probability that you can calculate certain probabilities with. So let's start with some examples, and that's pretty much what we do in the lecture today is we go through some examples of some of the different things you should have read in the notes. So I like to start with some counting principles because we do use some counting principles as we move through the probability material. So it's important that you just have a basic understanding of some counting principles, including the idea of a permutation and combination. So here's just a simple example of a counting principle problem. It says to buy a computer system, a customer can choose one of 5 monitors, one of 2 keyboards, one of 4 computers, and one of 3 printers. Determine the number of possible systems that a customer can choose from. Well, if you think about this, basically whenever you do counting problems, it's always a multiplicative relationship. So if there are 5 options for monitors and 2 options for keyboard, then you have 5 times 2, or 10 options for the combination of a monitor and a keyboard. So whenever we're dealing with 4 components here, we're dealing with a monitor, a keyboard, a computer, and a printer. You just use that same principle. So you take 5 monitors times 2 keyboards times 4 computers times 3 printers, and that gives you 120 options of computer systems to choose from. It's important to note that when we go through these counting principle problems, it's always really this multiplicative relationship where you look at basically how many options are there for the first item, times how many for the second, times how many for the third, and so on. Here's another example. Suppose that in the Olympics, there are 48 competitors swimming in the 100-meter freestyle. In how many ways can a gold, silver, and bronze medal be awarded? So, there's actually a couple ways to think about this. First of all, whenever you deal with these kinds of scenarios, you need to think about whether or not the order matters. Because sometimes the order of the outcomes matters and sometimes it doesn't. And that's really what distinguishes between the idea of a permutation and a combination. So the way you think about that is we're selecting 3 individuals here, right? Because we're going to select an individual to get the gold, an individual to get the silver, and an individual to get the bronze medal. And because of that, the order does matter. And the reason why I say the order matters is because person A getting the gold medal and person B getting the silver is a different outcome than person B getting the gold medal and person A getting the silver. It matters who gets which medal. So because of that, who gets the gold matters, who gets the silver matters, who gets the bronze matters. So because of that, the order matters. You're not just selecting 3 people and all 3 get the same award. So because of that, here the order matters. That makes this a permutation. With permutation problems, you have a couple options. You can just use the basic counting principles here, actually. And you can just say, well, there are 48 possibilities for the gold medal. That leaves 47 people to choose from for the silver, and that leaves 46 for the bronze. So you can actually just take 48 times 47 times 46, and that will give you the number of possibilities in this case. The other way to do these with permutations, and of course you should have seen this formula in the note. This is the formula for permutations when you have n objects and you're selecting r of them. So the way this works is you take n factorial over the quantity n minus r factorial. So in this case, n would be 48 because there are 48 competitors. That's the number of objects you're choosing from. And you're choosing 3 of them because you're choosing one person for the gold, 1 silver, and 1 bronze. So that means r here is 3. So basically you just plug in. So you end up with 48 factorial over 48 minus 3 factorial. So if you're going to use this equation, what you want to do, of course you can type this in your calculator as it is, but if you're going to do this by hand, you want to make sure that you cancel out in order to get what you need. And because 48 factorial is over 45 factorial, we know that we can actually cancel out 45 factorial because 48 factorial is equal to 48 times 47 times 46, and then everything else can just be written as 45 factorial. That allows your 45 factorials to cancel, and you're just left with what we mentioned earlier. You're left with 48 times 47 times 46, which gives you, in this case, 103,776 options. So if you'll notice what the formula does, the denominator of the formula essentially just cancels out what you don't need. Since we only need the first 3, we're only selecting 3 individuals in this permutation. That means that we basically only keep the first 3 numbers, 48 times 47 times 46, which is by definition and by what we just talked about in terms of counting principles, what we should have here when we do this permutation. Here's another example. A high school football team has 39 players. In how many ways can 4 captains be selected? So here we have 39 individuals and we're selecting 4. Now in this case it's different because in this case, notice that the order does not matter. And what I mean by that is it doesn't matter what order you get the 4 captains in. All it matters is what 4 people I end up with. So I'm just looking for a group of 4 people. The order of those 4 people do not matter here. So that makes this different than the last one. This is a combination problem rather than a permutation problem. So with combination problems, I highly recommend that you just use the formula because you lose the ability to just list out the outcomes and multiply them because you have to get rid of the arrangement of, in this case, these 4 outcomes. So you can actually do it like you would do a permutation problem and then divide by r factorial, and that will give you the right answer. But if you're going to go through all that, it's really best to just use the formula. So the formula for the combination looks very similar to the permutation. The only difference is, and I kind of already mentioned this, is you'll see that extra r factorial in the denominator. So in this case, we have 39 individuals, so that means n is 39, and we're selecting 4 of them. That means r is 4. So when you plug these into the formula, you end up with 39 factorial over 4 factorial times the quantity, 39 minus 4 factorial. So we're going to do a similar thing here. When we take that 39 minus 4, we're going to get 35 factorial there. So we want to make sure that we cancel that out. So when you rewrite that 39 factorial, we're just going to rewrite it as 39 times 38 times 37 times 36, and then times 35 factorial. And that way we cancel out that 35 factorial in the denominator. That leaves you with still 4 factorial, or 4 times 3 times 2 times 1 in the denominator. So if you want, you can actually go ahead and cancel some more here. For example, you could take 4 and divide it into 36 and cancel that out and then multiply. Sometimes I do it that way. But once you get down to this point, it's not that bad. You can really just plug it in your calculator. And if you do this, you'll end up with 1,974,024 over 24. You divide that out, you'll get 82,251. So that's your typical combination problem. So it's very important when you look at these permutations and combination kinds of problems that you really do distinguish between the two. You got to make sure you understand whether or not the order matters, because that tells you which formula to use, whether or not to use a permutation or a combination formula, because in a permutation the order does matter, and in a combination the order does not matter. Okay, let's get into some probability. We're just going to look at a simple scenario, and that's a lot of what we look at in this section, just kind of really basic scenarios so that we can make sure we get a good grasp on the idea of probability and its rules. So suppose here that we roll a die and we flip a coin. So let's start with how many possible outcomes are there. And here's your first application of accounting principle. We use exactly the same ideas as what we just talked about. How many possible outcomes are there? Where you have two operations. We call these operations within an experiment. The first operation is we're going to roll a die. The second operation is we're going to flip the coin. So when we roll the die, we have 6 possible outcomes. When we flip the coin, we have 2 possible outcomes. So once again, that's just a multiplicative relationship. It's just 6 times 2, which gives us 12 outcomes. So if you're just simply asked for how many outcomes there are, you just use those counting principles in order to figure out the number of outcomes when you're given a scenario like this. If you're asked for the sample space is actually a list of those outcomes. So we know there's 12 outcomes, but what are they? There's a couple ways you can do this here. The two common ways that we would do this, well, there's really 3 common ways we'd do it. We'd either just list them out. If you get good at this, you can pretty quickly figure out what the 12 outcomes are going to be. We can also use what's called a tree diagram here. And the other option would be to just use a table. So one of those 3 is how we should come up with our sample space. So I'm going to start with the idea of a tree diagram. So what a tree diagram does is it just basically starts at a single point, and then you basically branch out for the 6 outcomes to start. And then from each of those outcomes, you branch out to the 2 outcomes when you flip the coin. So this is what a tree diagram looks like in this scenario. So you can see you start at that point and you branch to 1, 2, 3, 4, 5, or 6. Those are your outcomes when you roll the die. And then off of each of those, if you roll a 1, you have 2 possible outcomes for the coin, either heads or tails, and I'm just going to denote those as H or T. And feel free to do that whenever we do these kinds of problems. It's very common that we'll abbreviate things. So for things like heads and tails, you can just use H and T. If you're dealing with red, green, and blue, you can use R, G, and B. So you can abbreviate things appropriately. So off of the 1, notice we have heads and tails. And then if we get a 2, we could get heads or tails. So off of each of those outcomes for the die, of course, you have 2 possible outcomes for the coin. If you count that last column of H's and T's, you'll notice there are 12 of them. That essentially is the 12 possible outcomes for this experiment. So the way we read this is if you start at the top, we call those the trailing branches of the tree diagram. The trailing branches are where we do our last operation, which in this case is flipping the coin. So if you look at that first H at the top, the way you get there is if you follow the branches, you get a 1 and then you get an H. The second outcome is right under that where you have the T and you get a 1 and a T. So if you go through, you can actually list out these 12 outcomes, which are 1H, 1T, 2H, 2T, and so on. So these are the 12 outcomes if you list them out. Like I said earlier, once you get good at this, you kind of get the pattern and you can just list out the outcomes without actually creating the tree diagram. But the tree diagram is kind of nice because it just makes sure you don't miss any outcomes or repeat any outcomes, which sometimes I'll see people make that mistake. So the tree diagram is a good way to get around that. So this is really 2 of the ways that we can write our sample space. You can either create the tree diagram, or you can just list out the outcomes. Let's talk about the third way. So the third way is to create a table. So for a table, you just let the columns, whenever we have 2 operations like we do here, you just let the columns of the table represent one operation and the rows of the table represent the other operation. So here, I'm going to let the columns of this table represent the outcomes whenever I roll the die, and I'm going to let the rows of the table represent the outcomes when I flip the coin. And once again, you get these same 12 outcomes. You can see each cell within the table represents a possible outcome. Those are the 12 outcomes in the sample space. If you're going to use a table when you have more than 2 operations, then you have to combine a couple of the operations. For example, if I were to roll a die and then flip a coin twice, then I could still let the columns of the table represent rolling the die, but then I would have to let the rows of the table represent flipping the coin twice rather than just flipping it once. So you would have to look at the possible outcomes when you flip the coin twice and let the rows represent those outcomes. So it gets a little more messy in a table when you have more than 2 outcomes. So the tree diagram, the table, just listing them out, all those are good options. It's nice to just know how to figure out how many outcomes you should expect using the counting principles, because that'll give you a good feel for whether or not you have the correct answer, of course. Okay, once we get the sample space, then we can start dealing with probability. So we're going to define a couple events. The way we define probability is we define it in terms of some event. Events are typically denoted by just capital letters from our alphabet, so it'll be like A, B, C, D, whatever, however many we have. So here we have 2. We define event A as the die being either a 5 or a 6, and we define event B as the coin being tails. So you can see that I identified A in blue, and I did it in the table as well. You can see those last 2 columns where you get either a 5 or a 6. Those are the outcomes in this sample space that satisfy A. And I did the same thing with B. I did it in green. B is the coin is tails, and that's that bottom row represents the coin is tails. So we'll start with what's called simple probabilities. So if you're just asked for the probability of an event, like the probability of A or the probability of B, we call that not because it's simple, but we just call that a simple probability because you're just finding the probability of an event. There are really 5 probabilities that we calculate in this class, which are the simple probabilities, then we have complements, we have unions, intersections, and we have conditions. So those are the 5. The simple probabilities are when you're just asked the probability of some event. So the way probability works in general, which you probably already know this, but you basically take the number of outcomes that satisfy the event over the total number of outcomes. So the denominator here, there are 12 outcomes, so the denominator here will always be 12. It will always be the number of outcomes in the sample space. For the numerator, you just figure out, well, how many of these outcomes satisfy A? So A is that I get a 5 or a 6. It's those last 2 columns. And you can see that there are 4 outcomes there. You get either the outcomes that satisfy this are 5H, 5T, 6H, and 6T. So we have 4 outcomes that satisfy that. We'll typically write probabilities as decimals. So you can see that we write that as just 0.333, basically 1/3. The probability of B is basically that bottom row. We already know the probability of getting tails is 1/2, but if we use the sample space here, then the denominator of that probability is, of course, 12. There are 6 outcomes in that bottom row, all those 1T, 2T, 3T, 4T, 5T, and 6T. All of those satisfy getting tails on the coin. So that means we have 6 over 12, or 0.5 as our probability. Next, we'll deal with the idea of a complement. So when you see the bar over top of the event, there's a couple ways to define complements, but I'll typically define complements with a bar over top of it. Sometimes you'll see it subscripted with a little c. Sometimes you'll see a prime. So it depends on what book you look at. Different books will do it different ways, but typically whenever I ask complement questions, I'll just put the bar over the event, and that is read the probability of a complement. The complement's a simple idea, but it's an important idea. The complement of A basically means what's the probability we get something that is not in A. So the complement of A is everything not in A. The reason why this is nice is because, or the reason why it's important is because sometimes it's actually easier to find the probability of a complement than it is to find the probability of A. And if you're in that scenario, then what you can do is you can just take 1 minus the probability of A, because what we know is we know the probability, the total probability in a sample space is 1, right? Because if you take, what's the probability you get an outcome in the sample space? Well, you always do. That's 12 out of 12. 12 out of 12 is 1. That's the max a probability can be. You always get an element from the sample space. So that means if we take the probability of A plus the probability of a complement and add those together, then we're getting everything in the sample space. So those 2 things have to add to be equal to 1. So one way to calculate the probability of A complement is use what's called the complement rule and just take 1 minus the probability of A, and that'll give you the probability of A complement. But if you know either one of those, if you know the probability of A or the probability of A complement, you can always get the other one because they must add to be equal to 1. And if it's easier to calculate one than the other, then sometimes we might calculate the complement in order to find the probability of A. And you'll actually see an example of that later on. So in this case, I just used the complement rule. I took 1 minus the probability of A, which is 1 minus 4 over 12. That gives you 8 over 12. You can also look at the sample space and see there are 8 outcomes not in A out of the 12, and that will give you that probability of 0.667. The probability of B complement works the same way. We can just take 1 minus the probability of B, and that in this case will give us 0.5. The next one that we're going to do is what's called the intersection, and you can see it's the way we read this is the probability of A intersect B. So it's kind of an upside down U that we use for that intersection symbol. So the intersection means it's essentially the overlap between A and B. So whenever we read this, we're looking at everything that satisfies both A and B. So the intersection is kind of like the AND. It is everything that satisfies both A and B. So what that means is the die has to be a 5 or a 6 and the coin has to be tails. Well, if you look at the table here and you look at the overlap, that means the tails are that bottom row. The 5 or 6 are those last two columns, so there's only 2 outcomes that satisfy that. The 2 outcomes that satisfy A intersect B is the 5T outcome and the 6T outcome. Those are the only 2 outcomes where the die is a 5 or a 6 and the coin is tails. So we have those 2 outcomes, 5T and 6T. So that's where your numerator comes from. Your numerator is 2 of the outcomes out of the total of 12, and that will give us that overlap of 0.167. The union, so we read this one, the probability of A union B. So you can see the union and intersection symbols. One is just flipped upside down. The union symbol looks kind of like a U. And we read that the probability of A union B. So there's 2 ways to calculate this. First, let me talk about what it is. So the intersection, as I said, is kind of like the AND. You have to satisfy both A and B. The union is kind of like the OR. So the probability of A union B is really the same as the probability of A or B. So to satisfy the union, you have to satisfy either A or you could satisfy B. So anything in either one of those outcomes would satisfy it. So you can always use the table, and you can go up to the table and you can see that you have those 4 outcomes that satisfied A. You have those 6 outcomes that satisfied B. But be careful, don't just take 4 plus 6, because 2 of those outcomes are in both A and B. And we get that from the intersection. So you got to be careful about that overlap there. So if you count those outcomes, you will see that there are actually 8 outcomes in the sample space that satisfy A or B. So you can do this with the sample space. The other way that you can do this is you can use what's called the addition rule. The addition rule is very useful in these kinds of scenarios. That's what I show you here. You can see that I say the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B. You have to subtract out that intersection, otherwise you're going to count the overlap twice, because you're going to count it once whenever you calculate the elements in A and another time when you calculate the elements in B. So you got to subtract those out so you don't count them twice. And you can see the way this works is you just get 4 plus 6 minus 2, which is 8 over 12. That's that 0.667. That is the probability of A union B. And by the way, I don't really care if you use the rule or if you use the sample space. As long as you do it in a proper way, that's really what matters. In this case, you can use either one. The last type of probability that we deal with is what's called a condition. So the way we read this one, if you know, a vertical line in mathematics is typically read as given. So we just read this as the probability of A given B. So this means given that B has occurred, what's the probability of A? So once again, there's a couple ways to do this. You can use the rule. You can also just figure this out if you think about it. So given B means that the coin is tails. If the coin is tails, that means that the denominator here is no longer 12. So this is the time that the denominator changes. Notice in every other probability, the denominator has been 12. But when you have that condition, the condition actually changes your denominator. So given that B occurred means we know that we got tails whenever we flip the coin. That means I only now have to deal with those 6 outcomes where we got tails on the coin. So basically the bottom row of the table, just where we have tails. And then you say, out of those outcomes, how many satisfied A? And it's just those last 2, 5t and 6t, so you end up with 2 out of 6. And you can see that's how this works out. It's 2 over 6, which is 0.333. That's one way to do it. The other way to do this is use what's called the conditional probability rule. The conditional probability rule says you take the intersection divided by the probability of the condition. So in this case, that would be the probability of A intersect B over the probability of B. And I highly recommend that you keep things in fractions here until you get to the end, because otherwise you'll get some rounding error. So when you do this, you get 2 over 12 for the probability of A intersect B. We just pulled that from up above. And for the probability of B, you get 6 over 12. Well, the 12s cancel, and you just get 2 over 6, which is what we said before. That's 0.333. And the way this rule basically works is it says the denominator is the probability of B. So the denominator essentially turns out to be 6, which is the number of elements in B. The numerator, the probability of A intersect B, is the overlap. That's those 2 elements that are in B but are also in A. So that gives you that 2 out of 6, and that's the way the rule works. It's important to note that with conditional probabilities, it does matter what order the events are in. Like with intersection and union, it doesn't matter. If you write the probability of A intersect B, that's the same as the probability of B intersect A. Same thing with union. But with conditions, it matters because it really does matter what your condition is. So let's look at this last one, the probability of B given A. So the probability of B given A, numerator stays the same. It's still the overlap, the probability of A intersect B. But the denominator, notice, is the condition, the probability of the condition. So the denominator in this case would be the probability of A. And that's one thing you got to be careful of with this rule. Whatever is after the line, the probability of that event, that is the denominator. So this one works very similar. You just take 2 over 12, which is your numerator, probability of A intersect B. The probability of A was 4 over 12. That gives you 2 over 4, which is 0.5. So those are your common probabilities. Those are the ones you need to be able to calculate in this section. The simple probabilities, complements, intersections, unions, conditions. Those are the ones. There's a couple terms that are important that I want to mention here. The 2 terms that I'm going to talk about is what mutually exclusive is, and then what independent events are. So it's nice to know when you're dealing with events if they are mutually exclusive or if they're independent or dependent, and commonly these are questions that I will ask. So if I ask, are A and B mutually exclusive? In order for A and B to be mutually exclusive, that means they cannot happen at the same time. So it's really a simple idea. Mutually exclusive just means they cannot happen at the same time. So in this case, can you get a 5 or a 6 on the die and get tails on the coin? And of course you can. Right? In this case, they can happen at the same time, which means these are not mutually exclusive. Now, mathematically, what's important is you want to make sure you look at this probability, because the probability of A intersect B is the probability that these do occur at the same time. So all you have to do to determine whether or not events are mutually exclusive is just look at this probability, the probability of A intersect B. If this probability is 0, 0 would mean they cannot happen at the same time. That would mean they were mutually exclusive. However, as we already mentioned, in this case, this probability is not 0. So that means the answer to this question is no, these events can happen at the same time, and the probability of them happening at the same time is actually 0.167. So in order to determine whether or not you have mutually exclusive events, all you have to do is look at the probability of that intersection. The other relationship here that's important is whether or not your events are independent. So independence is a little more messy. Two events are said to be independent if the occurrence or non-occurrence of one does not affect the probability of occurrence of the other. So that's a little difficult to just quickly understand what it means when you first hear it, but that's what it represents. It's basically, does one event occurring affect the probability of the other event occurring? That's what independence is. So sometimes you can just kind of think about it. In this case, you actually can. You can think about, does what I get whenever I flip the coin, does that have an effect on what I get when I roll the die? And of course it doesn't. There's no effect there, which means these are going to be independent. But let's talk about it mathematically. In order to determine whether or not events A and B are independent, the thing that you want to look at is you want to look at these two probabilities. You want to compare the probability of A, which we already showed to be 0.333. You want to compare that to the probability of A given B, which is also 0.333 here. They're equal. So what this means, if you compare these two, is notice that the second is the condition. Given that B occurred, the probability of A is 0.333. Well, that is the same as the probability of A. That means that the fact that we conditioned it on B did not change the probability. So the fact that B occurred did not change the probability of A here, which means these are independent. So the easiest way to tell whether or not two events are independent is just compare these two probabilities. If the probability of A equals the probability of A given B, then they're independent, as they are here. If the probability, if they're dependent, that means these two will not be equal, because that means B occurring changed the probability of A. It did have an effect, which means these two would not be equal. So the answer here, yes, getting tails on the coin has no effect on the probability of getting a 5 or a 6 on the die. So therefore they're independent. So this one you can really just think about. You know what you get on the coin is not going to affect what you get on the die. But lots of times it's really important that you actually compare the probabilities, because when you compare the probabilities, you'll know for sure whether or not they're dependent or independent. Okay, let's look at one more example and run through these one more time. There are two common ways that we look at probabilities. One way is like we did here, where we have a simple experiment and we actually identify the sample space and we have all the possible outcomes, and then we calculate probabilities from the outcomes from the experiment. The other way will be something like this, where we actually have something that's given to us, like a contingency table like you have here, and we'll define events in terms of the contingency table. So we have this group of 36 people. They're identified based on whether they're male or female, and then their political preference, Democrat, Republican, or Independent. We have two events defined. We're going to define event A as being female, and that's in green, so just like the last example. And we're going to define event B as the individual identifying as Democrat, and that is in blue. So we're just going to do the same thing here, but now notice these outcomes are based on frequency. So we have this group of 36 people. We look at the frequency for these categories, and then from that, we're going to calculate probability. So let's run through the same probabilities as we did before. It works basically the same way, only now you're using the numerical values within this contingency table. So the probability of A is the probability that we select a female. Well, we know the denominator is 36 because there's 36 people that we're dealing with here. Out of those, 16 are female, so that's just simply 16 over 36, which is 0.444. The probability of B, the B is that the individual identifies as a Democrat. 18 people identified as Democrat out of 36, so that is 18 over 36, or 0.5. The complements work the same way. You can just take 1 minus the probability of A. That's an easy thing to do here. You take 1 minus 16 over 36. That's 20 over 36, which is 0.556. B complement, same thing. 1 minus the probability of B. That will give you 0.5. The intersection. So the intersection here, we're looking at the overlap. So same as before here, we have to look at how many people satisfy both. So how many people are both female and identify as Democrat. So if you look at that row for females and where it intersects for that column of Democrat, you'll see that number 7 there. So there are 7 people that are both female and identify as Democrat. That means 7 over 36, which is 0.194. The union, here I would highly recommend that you just use the addition rule. We already know the probability of A, the probability of B, and we know the intersection. So you can simply just take those and plug them into the addition rule. So you get basically 16 plus 18 minus 7, which is 27 over 36, which is 0.75. You can also do it from the table, but I think it's way easier if you just use the addition rule in these kinds of cases. The conditions. So I'll show you the conditional probability rule here. I would probably actually do these with the table because I think it's easier than actually using the rule. But you can do it either way. A given B means you're only dealing with Democrats, so that means you're dealing with the column of Democrats. The denominator is 18. There were 18 Democrats. Out of those 18, 7 were female. So I would just take 7 over 18 and get that 0.389. Of course, you can see if you use the rule, you'll get the same thing. The rule will always work, so if you're ever in doubt about how to calculate the probability, use the rules because those are safe. Those will always work as long as you do the math right. If you flip this around and you say the probability of B given A, that means given A means you're dealing with females. That means your denominator is 16 because there are 16 females. Out of those 16 females, 7 identify as a Democrat. So that's 7 over 16, which is 0.438. And once again, you can also use the rule as you see there. You'll get the same thing. You get that 0.438. If we look at whether or not these are mutually exclusive or independent, let's start with the idea of mutually exclusive. Can they occur together? Well, can someone be both a female and Democrat? And of course they can. So that's obvious. But mathematically, we want to look at that probability of A intersect B. That would give you that 0.194. So that 0.194 obviously is not 0. We have a 0.194 chance of someone being both female and Democrat. So of course, no, these events can happen at the same time. So they're not mutually exclusive. Are they independent? So this is one where you really do have to look at the numbers. Because I could actually change the numbers on here and I could make the numbers so that this is dependent, or I could make the numbers so it's independent. In one group, being female might affect whether or not someone identifies as a Democrat. In another group, someone being female might not identify or might not affect whether or not someone identifies as being a Democrat. So this may or may not be the case. This is not a situation where you can just look at the variables and say, yeah, I know whether these are dependent or independent. So you got to look at the numbers here. So as we mentioned before, the numbers that you want to compare is you want to look at the probability of A as compared to the probability of A given B. And you'll notice here that these are not equal. The fact that they're not equal tells you that given that B occurred, the probability of A changed. So since these are not equal, that means these are not independent, these are dependent. The fact that B occurred changed the probability of A. And you can also look at these as the probability of B equals the probability of B given A. It's the same relationship. You can look at either one. But you can see here that these are not independent. These are dependent. It's important to look at the probabilities. It would not be clear if being female impacts the probability of being a Democrat without comparing the probabilities. So make sure you compare the probabilities in these kinds of scenarios. Like I mentioned before, you can change the numbers here and you can make these dependent or independent, especially when you look at these contingency tables like we have here. The last example. So the last example really deals with using the multiplication rule, which we haven't talked about. And then it goes back to the idea of the complement rule. So suppose the box contains 3 red, 3 white, and 5 blue marbles, and we're going to find some probabilities based on this. So suppose that you draw 3 marbles with replacement. What is the probability that all 3 are blue? So the way you think about this. So I always kind of think about this as we're drawing 3 marbles. So we have 3 spaces to fill. So lots of times I'll just draw 3 lines and say, I'm going to fill these spaces. I got to figure out the probability of each one, and that's where the multiplication rule comes in. You basically find the probability that the first marble is blue, you find the probability the second marble is blue, you find the probability the third marble is blue. And then once you do that, by the multiplication rule, if you multiply those together, that'll tell you the probability that they're all blue. That's the way the multiplication rule works. When you do a series of things, you find the probability of each one, multiply them together, that gives you the probability they all occur. There's one other thing that I should mention here. It says, if we draw 3 marbles with replacement. So when you read these kinds of questions, it's very common that you'll read and it'll say with replacement or without replacement. So those terms mean exactly what they say. With replacement means once I draw the marble, I'm going to put it back in and then I'm going to randomly draw another marble. Without replacement would mean once I draw a marble, I'm going to keep it out and then I'm going to go ahead and draw another marble. So the way this works, in this case, by the multiplication rule, is we say, well, the probability that the first marble is blue, there are 5 blue marbles out of 10, right? So that first 5 over 10, that's the first draw. The second 5 over 10, since we're doing this with replacement, we're putting it back in. That means the probability the second one is blue is also 5 over 10. The probability the third one is blue is also 5 over 10. So we basically just get 5 over 10 times 5 over 10 times 5 over 10. That'll give you the probability that they are all blue, which in this case gives us that 0.125 probability. The only difference in this next question is what happens if we do this without replacement. So if you do this without replacement, it does change things. It changes the probability. Now, the probability the first one is blue is still 5 over 10. But the probability the second one is blue changes. And the reason why it changes is because if you draw a blue one out on the first draw, then you only have 9 marbles left in there and only 4 of them are blue. So because of that, the probability has changed when you go to draw that second marble. So when you do things without replacement, what you do is you assume that the first one is blue, and you calculate the probability. Then you assume the second one is also blue, and you calculate the probability that it was blue. Then you assume the third one is also blue, and you calculate the probability that it is blue. Then you multiply those together, and that will give you the total probability. So in this case, your probability is going to look like this. The probability the first one is blue is 5 over 10. But once we take that blue marble out, the probability the second one will be blue. There will now be 4 blue marbles out of 9 left. So the probability the second one is blue is now 4 out of 9. Assuming those first 2 are blue, that only leaves 8 marbles, 3 of which are blue for the third draw. So the probability that third marble is blue is 3 out of 8. Once we identify those probabilities, then the multiplication rule works the same way. We just simply multiply, and we get that probability of 0.083. The last question looks like this. If you draw 3 marbles without replacement, so same as the previous scenario, what is the probability that at least one of the marbles are not blue? So this is one of those scenarios where if you think about it directly, you have quite a bit of work to do to figure this out. Because if we want the probability that at least one of the marbles are not blue, well, the deal is since we're drawing 3 marbles, it could be the first marble that's not blue, or it could be the second marble that's not blue, or it could be the third marble that's not blue. It could also be the first 2 that are not blue, or the last 2, or the first and last. It could also be that all 3 marbles are not blue. So there's multiple ways for this to happen. There's a bunch of different ways that we could end up with at least one marble not being blue. To calculate this directly, you would have to calculate the probability of all of those and then add those together, and that would give you the proper probability. But there's an easier way to do this. This is where the complement rule comes in, and it's where it's very useful. If you think about the complement of at least one not being blue, well, the complement of having at least one of the marbles not blue, the opposite of that, or the complement of that, is that they're all blue, right? So since the complement of this probability is that they're all blue, that means we can just calculate the probability they're all blue. That's just one calculation. Subtract it from 1 by the complement rule, and that'll give us the probability that at least one is not blue. So we've actually already calculated the probability that they're all blue. We did that in the previous one. We got that to be 0.083. So if you want the probability that at least one is not blue, all you have to do is use that complement rule. Just take 1 minus that 0.083, and that will give you the correct probability. So the probability for this is 0.917. And like I said earlier, this is why the complement rule is so useful. It's a really easy rule, but it's also very important because in these kinds of scenarios, you would want to use the complement rule rather than trying to find it directly. So this section really is, and I've said this a few times, but it focuses on make sure you understand just those basic counting principles. Make sure you understand the 5 common probabilities: simple, complements, unions, intersections, conditions, and then make sure you understand the rules. Things like the complement rule, the addition rule, the complement rule, the addition rule, the conditional probability rule, the multiplication rule, those different rules, those are important to be able to apply. That's what we cover in this section. That is the end of section 4.